Hi everyone, today's video is called What Lies Behind the Same Shape, and this is continuing our work with transformations. We're going to add a new transformation today, and I've got the first exercise up here on the screen, but let's just refer to what's in the box here first. It says two geometric figures are said to be similar if they have the same shape but not necessarily the same size. And all the transformations that we've worked with so far have preserved the shape and the size of the objects. And we said if that happens, if you do a reflection, a translation, or a rotation, they are the same size and the same shape, and we said that those two shapes would be congruent. Well, this is the first one that we're going to talk about where the size or the shape may not be preserved. Alright, so one thing we're adding in is this word similar right here. I'm underlining it up here, and this is different than congruent. Alright, so if we look at exercise number 1 down here, it says, are the following pairs of shapes similar? Well, if they are the same shape but not necessarily the same size, then we can say they are similar. So if I look at these first two on the left, they look to be the same shape, but obviously this one on the right is bigger. So I would say yes, these two are similar right here. So I'd like you to write that in your packet, that those two are similar. Alright, if I look at the next set, obviously these are two shapes with 4 sides here, and I want to know, are they the same shape but not necessarily the same size? Well, at first glance you might say, you know what, yeah, those are the same shape there, but if I actually measured these, I see this one has all 4 sides are the same. That's what these little hash marks mean. Whenever I put a little hash mark on a side, it means that it's the same size as another side with that same number of hash marks there. So this one I would classify as being a square. Alright, and this one, it's pretty obvious to see that the sides of these are not all the same, or of this one I should say. So I'm going to put 2 hash marks here and 2 hash marks, so make that a little bigger, 2 hash marks there. So that means these 2 sides are the same, alright? But these 2 sides, I'm going to put 3 hash marks on each one of those because I took my ruler out and I measured it, and those 2 are the same, alright? So does that constitute being same size, but not, or sorry, same shape, but not necessarily the same size? Well, I'm going to call this one a rectangle, alright? And do they have the same shape? Well, they have 4 sides. They have 90-degree angles in each of the corners. So even though this one has 4 equal sides and this one doesn't, they still constitute the same shape. But again, they're not necessarily the same size. So again, I'm going to say yes, they are similar. Alright, so you write that in as well. And take a look at the third set here. These are 5-sided shapes, and I measured them again, and all of these are the same size, all these little segments here. And I measured this one, and they happen to be the same size as well. Alright, so they're not only the same shape, these are pentagons by the way, they're not only the same shape, but they're also the same size. Well, that actually makes them congruent, but if they are congruent, well, that means they are similar as well. Okay, so they can be the same size, but they don't have to be similar. Alright, and let's take a look at this last set here. This is the set of images that I would say would not be similar because they are obviously not the same shape. Alright, this little smiley face is really squished, where this one seems to be a perfect circle. So I would say no. Alright, not similar here. because they do not have the same shape. Alrighty, so pretty straightforward so far. This is the new term we're adding in right now. We're going to add another one in a minute here, but for two things to be similar, they have to have the same shape, but not necessarily the same size. Alright, so let me switch over to the next example here. And you notice we have another little box on your note packet, and it says a dilation. Now this is another new term for us. It's another transformation. So we've had reflections, rotations, and translations. And now we're going to add in the word dilation. Another transformation, and it says is a transformation of the plane with centers O. Okay, and just like rotations, we had it rotating about a central point O, or whatever point we name. And this also has a center point that we dilate about, but it says with a scale factor of R. Alright, and when you think of a scale factor, what reminds me in my head when I think of scale is I think of models. Alright, and I think of those little railroad train models, those trains that we used to play with as kids, or any kind of action figures, or any kind of even dolls that some of you may have played with. And what they've done is they've taken the real item, the real train or real person or what have you, and they've scaled it down. They've reduced everything by a factor. Alright, and that's what I think of when I think of scale factor. I kind of think of that as being a multiplier. Okay, I think of that word right there, because when you work with a scale factor, you're multiplying by that scale factor. Alright, so let me show you how it works here. Part A to exercise 2, you are given a segment that has a length of 7. So I can draw a little segment here. That's my line segment. I've got 2 points on each end, and we're going to call it AB. And it says that we will write, oh, that doesn't really make sense. We will write that as, okay, now I've got to fix that. We'll write AB equal to 7. Alright, so I'm just going to label it 7. If the segment AB is dilated by a scale factor of R equal to 3, well, what is the length of segment AB? Alright, well, very easily, think of the scale factor as being a multiplier, and we want to know the length of segment AB prime. I kind of missed that little prime up there. So what's happening is I'm going to start at A, but I'm going to multiply this segment 7 by a scale factor of 3. So what I'm going to have is I'm going to have a segment that goes way out to here, and it's going to go from A, and it's going to extend out to B prime. So now I'm looking for how long is this segment, AB prime. Well, very easy. Just take segment AB, which is 7, and I'm going to dilate it by a scale factor of 3. So it means I'm really going to just take 7 multiplied by 3. So 21 is the length of AB prime. Alright, if I want to write it over here, I could just say AB prime equals 21. How easy is that? Alright, let's do part B. If segment CD has a length of 5, alright, so let me make segment CD. I can make it C there and D there, and I'm going to label it 5. Now it said it's dilated by a scale factor of R equals a half. Oh, now this one's a little different. This is multiplying by a fraction. So already you should be saying to yourself, oh, that's going to make it smaller. If I multiply something by a fraction, a whole number, or a number greater than 1 by a fraction, it's actually going to make it smaller. So they want to know what is the length of CD prime. So CD prime is not even going to be as big as CD. So let's do it right over here. We're going to take CD, which is 5, and I'm going to multiply by a factor of 1/2. And if I multiply 5 by 1/2, I get 2.5. Alright, so CD prime is going to go to half of what CD did. Alright, so very easy. Again, I did the same thing. I just multiplied by that scale factor. So CD prime equals 2.5. Alright, so pretty easy so far. Let's skip over to exercise 3. Okay, let me get rid of that other. And now we have something a little more mathematical. And I'm going to turn on this one as well. Exercise 3 has 3 questions to it. And it's basically the same thing. What is the length of OP prime? And this would be from O all the way up to P prime here. What is the length of segment OP prime if the scale factor that segment OP was dilated is 3? Well, do the same thing. OP is 3, so there's the length of OP, and I want to dilate it by a scale factor of 3. So I'm just going to multiply it by 3. Well, OP prime, 3 times 3 is 9. So OP prime equals 9. There you go. And I could put a little curly brackets in here if I really wanted to and label that 9. Okay, how easy is that? Alrighty, let's do the second part here. I'm going to turn this one off and turn this one on. And here's the second question. I'm going to change this in your note packet because this is the same scale factor. I'm going to change this. I want you to take, oops, let me get that, there we go. I'm going to take this and cross out that 3, and let's make it into a 5. Alright, let's make that one into a 5 for me. Alright, so what is the length of OQ prime? So I'm going to start at O here, and I'm going to go all the way out to Q prime. If the scale factor used to dilate OQ is 4. Alright, well, OQ is 4, and I'm going to multiply it by the scale factor, which is 5, and I get 20. So OQ prime equals 20. And again, if you want to label it right on your paper here, make those little curly Q brackets, and that is 20. Alright, again, pretty straightforward. Now, one last one. We want to go the other way. We want to give you the length of something and say what is the scale factor. Okay, so that's no big deal. Let's turn that one on. And here we go. If the length of segment OP prime is 27, now in this case we're going to cross out this 3 up here because we're not going to use that anymore. We're going to say if the length of OP prime is 27, so I'm going to label that this to be 27, and the length of OP is 3, well, actually I can take that right off and make that equal to 3 again. Then what scale factor was used to dilate OP? Alright, well, this is more of an algebraic problem. What I don't know is the scale factor. Now, some of you guys, I'm sure, have already done this in your head, but I'm going to put this down because I don't know what something is, and usually in math, when we don't know what something is, we label it X. Alright? So if I take the length of OP prime, 27, and I do the opposite of what I did before, I divide by the scale factor. I don't want to put a 3 down there. I want to put the scale factor, which is the thing I don't know. Okay? And that should equal what I started out with originally. That should equal the length of OP. So I could set up an equation like this. Alright? Another way we write it would be like that. Alright? Those two say the same thing. Alright? And I'm going to solve for X here. Alright? And if I multiply on both sides by X, I'm going to do it right over here. I'm going to multiply by X. Well, over on this left side, the X's are going to cancel because this is really X over 1. And when I multiply fractions, then I can cancel on the diagonal. So I get 27 equals 3 times X. Alright? And again, if I want to solve for X, I want to get X all by itself, I simply divide by 3 on both sides. Alright? And that's going to give me X equal to 9. So the scale factor here is 9. Alrighty? Now, most of you guys could probably have done that in your head. You're saying, well, we're just doing the opposite of what we did before. So I take the 27 and I divide by 3. But I wanted to show you, our problems may get a little more complicated in the future here. So I wanted to show you exactly how to do it algebraically. All right, and I could have done the same thing with this equation that I wrote over here. Alrighty, so today, two things for something to be similar. Okay, let me turn this back on over here. Turn that one off and turn this one on. For something to be similar, they have to have the same size, the same shape, but not necessarily the same size. Okay, and the other item we wanted to work with today is whether something is a dilation. You know, how we figure out that scale factor and what is that going to be. So two things, pretty straightforward. Remember, the dilation is a new transformation. It's the only one that's going to change the size and shape of the object. So thanks for watching, and hope we all have a good night.